Applications of oxidation-reduction reactions. There are two main applications of redox reactions. They are different primarily in whether they occur spontaneously or not. In this lesson, we will look at some of the spontaneous reactions. These spontaneous reactions, as we have already learned, can be arranged to be voltaic cells. Some of the spontaneous reactions occur in nature, and we do not want them to occur. Let's look at several voltaic cells and see what they look like. The lead storage cell is the battery that is used in automobiles. It consists of a grid of lead metal in which is placed spongy lead on one side of the cell. Spongy lead is lead that has a lot of surface area, and a lead grid filled with lead-4 oxide on the other side of the cell. The liquid in the cell is sulfuric acid, H2SO4. The reaction at the anode is the oxidation of the lead metal to lead-2 ions. However, the presence of the sulfate or hydrogen sulfate ions in the solution causes the lead-2 to precipitate as lead-2 sulfate, a solid. This increases the acidity near the anode. At the cathode, the reduction of lead-4 to lead-2 occurs. The reaction also produces lead-2 sulfate and uses up hydrogen ions to make water from the oxygen in the PbO2. The net reaction is the reaction of lead metal with lead-4 oxide in the presence of hydrogen sulfate ions and hydrogen ions to make lead-2 sulfate and water. The advantages of this type of cell are: 1. The product is the same for both the oxidation and the reduction. 2. Most reactants and products are solids. And 3. No gases are produced. This gives a cell where both the anode and cathode can be in the same container because the reactants are solids and will not migrate. And it allows fairly easy recharging of the cell because there's only one significant product for the two half reactions. The disadvantage is that the battery is very heavy because of the density of the lead metal, and further, that the lead metal is toxic. The dry cell is not really dry, but does not contain a solution, as many cells do. It consists of a graphite electrode at the center of a paste containing manganese 4 oxide, ammonium chloride, and carbon. The other electrode is the zinc inner case. At the anode, zinc metal oxidizes to zinc 2+ ions, while at the cathode, the manganese is reduced from +4 to +3. In the process, ammonia gas is produced. The advantages of this type of cell are: 1. Its paste allows the cell to be rather portable, and 2. The paste is enough to separate the two half reactions because the reactants are both solid. The disadvantages are: 1. It produces a gas, ammonia gas. 2. The zinc case of the battery deteriorates as the reaction proceeds, sometimes causing a splitting of the case, allowing the contents to leak out. And 3. The acidic nature of the contents, ammonium ion is slightly acidic, is reduced as the reaction proceeds, which may affect the voltage. One way to deal with the last problem is to use an alkaline cell, which essentially does the same reaction, but in a basic environment. The cathode is MnO2 and graphite, and the anode is zinc and KOH. This battery contains a separator that keeps the two half cells apart. At the anode, zinc metal is oxidized to zinc ions, which precipitate with the hydroxide ions, forming ZnOH2. At the cathode, Manganese is again reduced from +4 to +3, but this time it produces OH-, which balances out the hydroxide that was tied up on the other side. The advantages are: 1. Mostly solid reactants and products, no gas produced. And 2. The basic nature of the contents is not affected by the reaction, so the voltage is more consistent. In a hydrogen-oxygen fuel cell, rather than burning the hydrogen to generate heat, which is then used to boil water, to make steam, to drive turbines to generate electricity, the reaction is employed directly to do so. Hydrogen gas is oxidized at the anode to make hydrogen ions. Oxygen gas is reduced at the cathode, in the presence of hydrogen ions, to make water. The net reaction is the same as the burning of hydrogen, but with the direct transfer of the electrons through an external circuit. This type of cell can employ any substance that we normally burn as a fuel. This is why we call this type of voltaic cell a fuel cell. The advantage of this type of cell over the burning of a fuel to boil water to run a turbine is that the energy of the reaction is converted into electric current much more efficiently than by burning the fuel in a power plant and transporting the electricity through power lines. The disadvantage is that it generates direct current rather than alternating current, DC rather than AC, which cannot be transmitted over long distances. One of the undesired spontaneous redox reactions is corrosion. Corrosion is most commonly linked to iron rusting. The formation of rust, iron oxides, and its flaking off weakens iron structures like bridges and tools, causing them to eventually fail to withstand the loads we are expecting them to bear. Iron oxidizes to Fe2+ as the metal becomes the anode of a redox reaction. The cathode is at some other place in the exposed iron, where oxygen comes in contact with the iron. The oxygen is reduced to oxide, O2-, and combines with the Fe2+ to make rust. Contrary to what many people think, it is not the water that rusts the iron, and it is not the salt that is put on the roads either. Both the water, by providing a medium for the transporting of the Fe2+ ions, and the salt, by providing a means of transporting charge, help the process of rusting, but are not the cause of it. The reaction is between iron and the oxygen of the air. How can we prevent this corrosion? There are several ways. First, we can prevent the oxygen and iron from meeting by coating the iron with something to prevent it from coming in contact with the air. Paint comes to mind and is often used. This also has the advantage of excluding water. Another way is to make the iron the cathode by running an electric current through the metal to force the iron to be the cathode. One final way is to bind a more active metal to the iron. Zinc is such a metal. When we give the iron a coating of zinc, the iron is said to be galvanized. Because the zinc is more active, the zinc will be oxidized in preference to the iron, making the zinc the anode, where zinc becomes Zn2+, and the iron becomes the cathode, where reduction occurs and the iron does not get oxidized.